now that we've looked at how the atom was discovered, we're going to look at how these elements get organized. So it's going to be a little bit more history. So in the 1700s, Dmitri Mendeleev really started looking at ways to organize the elements. In the 1700s, there was no good solution. So in the 1860s, Mendeleev, who was a teacher and a chemist, developed the first successful method for organizing the elements. So when Mendeleev was doing his research, he was writing a chemistry textbook and needed a way to organize the elements to help students learn about them. So he basically made a set of like playing cards for each element, one card per element, and on the card it had the element's name, its atomic mass, and any known properties or anything they knew about that element at that time. And so since they were in cards, he was able to arrange and rearrange these cards in many different ways, all the while he was looking for patterns. And when he found the pattern, he noticed that it was when the elements were placed in order by atomic mass. So Mendeleev's periodic table was organized by atomic mass. And so from left to right, what he noticed was that there was an increasing atomic mass, meaning the elements got heavier. In each row, he had 8 elements, and then the columns of the periodic table contained elements with similar properties. And so we call those columns groups, and they're the columns on the periodic table that contain elements with similar properties. Sometimes we call them families. And this one's a little easy for me to remember because I think of like a family tree or a tree in general is a vertical thing, just like a column. So it's important to note that these elements in families are similar, but they're not identical. Just like a family. They all have their similarities, but they're not identical to one another. So this pattern repeated. And so what we came up with was the periodic table of the elements. And it was arranged by increasing atomic number. That's the modern periodic table, the one we use today. However, Mendeleev's was organized by increasing mass. So anything that keeps repeating is referred to as periodic. So like the monthly phases of the moon, the daily cycle of night and day, even magazines are in a library are called periodicals, or newspapers are periodicals because they come out in a repeating pattern. So the periods on a periodic table are the horizontal, or the rows, that contain elements, and they range from metals on the left hand side to metalloids, and those are in the middle, and then all the way on the right hand side we have the non-metals. So this is how Mendeleev's periodic table looked. And so what you'll notice is that he left blanks, like here's a blank, or here. And he did this because he predicted that there were elements in the world that would eventually be discovered that could fit into these blanks. He was so sure of this idea that he could even predict the missing elements' properties. And those properties would be based on the location of the element on the periodic table. So for example, he predicted that a missing element in row 5 had an atomic mass of about 68, and it was a soft metal. And eventually, when gallium was discovered, he was found to be correct. And so this is an example of a good model, because good models allow for accurate predictions. So now we have our modern periodic table of the elements. So notice the color coding. Metals are blue, and they are on the left. The metalloids are the yellow, and they're located in between. Let's not call it middle, let's call it in between, because it's really not the middle. And then the nonmetals are located on the right. The one exception is hydrogen, and we'll talk about why that's an exception eventually. So the modern periodic table is organized by atomic number. And remember that the atomic number indicates the number of protons that an element has. Oh, right here. And that's unique for each element. So the atomic number will increase as you go from left to right across each period. So if we go back and look at this periodic table, you'll notice starting in this row, let's start in row 3, sodium has an atomic number of 11, magnesium is 12, all the way through to 13, and argon is up to 18. So they're increasing in atomic number within each row. And also increases from top to bottom within each family. So remember, the families are the vertical columns. And so when you look at it and you go down the vertical column, we start at 4 for an atomic number, and we end up at 88 down at radium. And so it increases within each family as well. So when we read the periodic table, we get some basic information. First of all, each element has its chemical symbol. So this is going to be a 1 or 2 letters that come from the chemical's name in either English or another language. Oftentimes that other language is going to be Latin or Greek. The first letter is always going to be capitalized. And the second letter, if there is one, will be lowercase. So, for example, lead has the symbol PB, and that makes sense, not so much in the English sense of the word lead, but in Latin, plumbum means lead. So that would be where we get the P and the B from. And so we have 3 classes of elements: the metals, the metalloids, and the nonmetals. And usually on a periodic table, these will be color-coded, much like our periodic table here, with the metals being blue, the metalloids this orangish yellow, and then lastly the nonmetals will be green. Some periodic tables will put the coloring in the symbols, so the symbols would be written, the font would be a different color depending on what class of an element it is. So each element, each period contains 1 more proton than the element before it. So that's that increasing. Elements change from metals to metalloids, and then lastly to nonmetals as you move across a period. So notice here we have the period starting with potassium. We start with the blue metals, and then it transitions to the metalloids, and then lastly we have the nonmetals. So period 1 contains 2 elements, whereas period 6 and 7 are so long that some of their elements actually get placed below the main part of the periodic table. So what I mean is, if we go back and look at this periodic table, this block down here, if we match up their numbers, we'll see that they actually should be plugged in right here. And so that would make periods 6 and 7 extend pretty much off the page. So they really just pull these 2 rows out and put them below as a formatting situation so that the periodic table fits on one page. Elements 114 and 116 became part of the periodic table in 2011. In 2015, 4 new elements were added, elements 113, 115, 117, and 118. However, they haven't officially been accepted by IUPAC. This is the big international chemistry organization of the world. So what they're doing right now is they're making sure, the scientific research is sound, this element really is stable, and so they are verifying those 4 elements. So some of those new elements, 113, Nihonium, which means Japan actually, because it was named by Japanese researchers. Element 115, Moscovium, MC, was named for Moscow. And scientists from Russia and the United States were involved with the discovery of Moscovium. Tennessine is based on Tennessee. Again, scientists from Russia and the U.S. were involved with that one. And then Oganesian is from Yuri Oganesian. And he is apparently a famous element hunter. So when we look at groups, there are 18 different groups. Remember, these are the vertical columns. And they have similar properties. So for example, all elements in that last group, or group 18, are colorless, odorless, and they are all gases. And they're also fairly non-reactive, meaning they're not involved in chemical reactions. So that was a quick little history up to the modern day periodic table for you, and we'll continue with this tomorrow.